Welcome to the lecture about SHAP values. SHAP is short for Shapley Additive Explanation. And today we want to get an intuition of additive feature attributions, understand the concept of KernelSHAP, being able to interpret SHAP plots, and talk about global SHAP methods. So remember that Shapley values in machine learning answer the question, how much does a feature J contribute to the prediction of a single observation? And for that, we used Shapley values from cooperative game theory. Let's do a short recap. So the idea was to compare a reduced prediction function of a feature coalition S with S, where you also have the feature J. So you have one prediction with the coalition S and one with the coalition S and the feature J. And we iterate over possible coalitions to calculate the marginal contribution of feature J to sample X. So the Shapley value phi J for feature J was the average over all possible orderings, and these are factorial of P, so where P is the number of features. And now for each of them, for each of the orderings, we look at the difference between the prediction difference between the coalition where feature J is included and the prediction where feature J is not included, which is then the marginal contribution of our feature J. If we do that difference for all possible orderings, and that's our Shapley value. So here remember that f hat is the prediction function and p the number of features. And non-existing features in a coalition are replaced by values of random feature values. So what we did here was to order the features, and we had S before our feature J, and then we feature J, and after that minus S. And we used that orderings to calculate the Shapley value. So for example, if we train a random forest on the bike sharing data with only 3 features, humidity, temperature, and wind speed, then calculate the Shapley value for an observation where the prediction is 2,500. So that's quite a low number of rented bikes for a day. And the mean prediction or the expected value of our prediction function is 4,500. And now for this simple data set with only 3 features, we can do that quite easily per hand. So we start with the empty set, and now we add humidity to that empty set. So without humidity, so we have the empty set as the coalition. So that means we get just the expected value as the prediction, because none of the features is in the coalition. And now if we add humidity, so instead of using the expected value, we use here the actual feature value for humidity, then the prediction is a little bit higher. And because the empty set can be defined in 2 possible orderings, so we could start with the temperature and then with the wind speed and then add humidity, or we could start wind speed, temperature, humidity, we get a weight of 2. We do the same for all other coalitions. So we start with temperature and then we add humidity, and we look at the difference in prediction after adding humidity to that coalition. And we're doing the weighting, and for the full coalition, we again have 2 options to order these 2 features and after adding humidity, and that's why we again have a weight of 2. And also note that if we have the coalition with all features, we end up with the original predicted value for that observation, because we take the actual observed values for all 3 features. And now to calculate the Shapley value, we will just take the marginal differences. So this we take from here, and this one we take from here, from here, this one from here, and we weight them by our weights, and that is our Shapley value. And in this case, it's 34. So you can already guess that the other two features will have a negative Shapley value because we are quite low compared to the expected value. And so the temperature gets quite a low value, so minus 1,600, and the wind speed minus about 300. After we do the exact same calculation for the other two features. And you also get that plot here on the right. So we see the true value, the average, and we see that wind speed has a negative value. So here is 0. So it drives the prediction down. Temperature also drives it down, and humidity drives it slightly upwards. And now we can write it in a way that we have our actual prediction minus the expected value is the sum of the Shapley values, which was that minus 1,942. And if we now, and these are exactly then the 3 Shapley values. And now we can rewrite that to have the prediction of the observation on the left-hand side, and we move the expected value to the right-hand side, and we can also call it phi 0. And we'll use that formulation for the SHAP values. Because here we want to find an additive combination that explains the prediction of an observation X by computing the contribution of each feature to the prediction using some estimation procedure, which should be more efficient than just calculating the Shapley values in the way we've just seen before. So, and for that, we start with a simplified and binary coalition feature space, Z, which is a binary matrix, which has as k rows, and k is now the number of possible coalitions, and p the number of features. And for each row, let's maybe do that by example. So here we have the empty coalition, so they're all 0. So humidity is not in, temperature is not in, and wind speed is not in. Here we have the full coalition, so everyone is in, everyone gets a 0. And if only temperature is in, only temperature gets a 1. And these rows, we call them small z prime. And the whole thing is the matrix capital Z prime. And we'll use that rows of this matrix in a way that we take a coalition, so that's one row of that matrix. And now we have that additive combination of our expected value and a multiplication of SHAP values with the rows of that matrix. So this is the null output, so the expected value. And here we have the attribution, so how much does feature J change the output for collision K? And the left-hand side here is now the marginal contribution of that coalition Z prime K. So the marginal contribution of that row in that Z, capital Z matrix. And here on the right-hand side, we'll find again the Shapley values, and together that's an additive feature attribution. So that's quite nice that we can write that in another way, but that doesn't help us with estimation yet, because we still need the Shapley values for that. So how to estimate them? And for that, we can use KernelSHAP. KernelSHAP is a kernel-based and model-agnostic method to compute Shapley values via local surrogate models. And we do that in 5 steps. So first, we sample coalitions. So that's similar as in the Shapley values. Then we transfer the coalitions into a feature space and get predictions by applying the machine learning model, compute weights through a kernel, fit a weighted linear model, and thus return the Shapley values. So now we go through it step by step. So for this first step, we sample coalitions. So we have again here our matrix, and we just sample rows from that matrix. So we could say just randomly, we might end up with this and this and this. But obviously, if we only have 3 features, then we only have 8 possible coalitions. So we don't have to do any sampling. So we will just continue with all of them. But if you have more features, then this will, as we have seen in the Shapley values, it will quickly get too large. And that's why we do a random sampling here. In the second step, now we look at those vectors of, so the rows of the matrix. And here it is 1 if this feature is part of the coalition, and it's 0 if it's absent. And if we now want to calculate predictions for these coalitions, we need to define a function mapping the binary feature space back to the original feature space. So here on the left, you have our binary feature space, so our binary matrix. And on the right, we have the matrix with original feature space. And what we want to do is that always a 0 maps to not included, and a 1 maps to included, meaning that we take the original feature value for that observation. So if, and here at the bottom, all 3 are included, we just take the feature values for that observation, and that will lead then to the original prediction. And if only wind speed is included, we'll take the feature value for wind speed, but here they have not included humidity and temperature. But what to do now about those values? And that's what we do here. We do a random sampling of observations, so as with Shapley values. So for all features that are absent in the coalition, so that have a 0 in that row of the Z matrix, we take some values from a random observation. So for this, we take a random observation, which has this value for humidity, this one for temperature, and this for wind speed. And in the empty coalition, we replace all 3. And in all other cases, we always replace the ones where we have a 0 in the Z matrix by that other random observation. And we can do that permutations multiple times. And then we can calculate the actual prediction of the model with these features. So this gives us, because all features are the same as from the observation, we get the original prediction. And here we get the prediction of the sampled observation, and we get a combination somewhere in between. So that's then our f hat, so that's our model of our hx, which is the function mapping the binary to the original feature space of a row in the matrix, are then here to the right, the values. And now we said we want to do some weighting. So we could do that without weighting, so just being a 1 for all of net. But the idea in SHaP is that we learn most about individual features if we can study their effects in isolation. So meaning a coalition size of 1. So there's only 1 feature in the coalition. Or at maximal interaction, meaning all features are included. But actually the one with all of them included is not so interesting, because then we cannot add our feature again, and we will just always get the original prediction. That's why we weight up the ones close to the 10. And now we calculate those weights by dividing the number of features by some by a nominal coefficient and the size of the coalition. So this is here we have the number of features, and here we have basically the coalition size and some normalization factors. And that gives us the kernel weight for our coalition Z, so a row of that matrix. So by example, we can calculate it here. So we have P equals 3. And if we now have two features, or if we now just have one feature in, so those are this, and this row, we will have 3 minus 1 is 2 over 3 over 1 times 1 times 3 minus 1. And this is 2 over 3 times 1 times 2. And this is 1 over 3. Right? So same as we have here. We can do the same calculation for still P is 3, and now size of the coalition is 2. So these are those 3. Then we get 2 over binomial coefficient of 3 and 2, which is also 3 times 2 times 3 minus 2, which is then 2 over 3 times 2 times 1. So same result. So also 1/3. That's why we have the same weights here for them. But that is just that just happens in the simple example. You will get different weights if you have a larger model. And you have that infinity weights for the 0 and the full coalition, but we will just ignore them and not use them as observations in the linear regression. But we have to use some constraint to have properties of SHaP satisfied. We'll talk about these properties a little bit later. So now we fit a weighted linear model. So a linear model where our Shapley values are the coefficients, and the Z matrix is our X. And that gives us, and we use weighted least squares to solve that. That gives us a P minus 1 dimensional linear regression problem. So what we do is we take our Z matrix, that's X, and we take our prediction, that's Y, and now our linear regression model is Y is X times phi, where phi is now our matrix, our vector of Shapley values, and we have an error term. And we can also see that here. So we have some intercept, which is phi 0, and this is phi 1. So the Shapley value for feature 1, and this is phi 2 and phi 3. And because we can solve it with least squares, this is an exact solution, and it gives us exactly the same Shapley values as with the original Shapley computation. And we can plot that in a nice way. So we see here the actual prediction of net observation. So this is f hat of x, so this value, and we get here our expected value of f of x, so that's the average prediction. And now we see that wind speed drives the prediction from the expected value down, and temperature drives it down even more, and humidity drives it up a little bit again. That's why we have here the small positive value for humidity, the large negative value for temperature, and also quite large negative value for wind speed. So SHAP values also have some property related to the axioms of Shapley values. And the first one is local accuracy. So here the intuition is if the coalition includes all features, then the attributions, so the Shapley values in the null output, sum up to the original model output. So basically, if you include all of them, you get the actual prediction. And this is similar to the axiom of efficiency in the Shapley game theory. That was that all the Shapley values sum up to the total payout. Here, the total payout is always the model output fx. And then we have missingness. So meaning a missing feature gets an attribution of 0. So for each row, when the feature is missing, it gets a Shapley value of 0. And we have consistency. So if we have two models, f hat and f prime hat, and if for f prime hat the prediction for coalition is larger than the one without the feature of interest, and this is if the difference between those two, so the marginal contribution in the model f prime hat is larger than the marginal contribution of the model f hat, then that means that the Shapley values of f prime hat are always larger than the Shapley values of f hat. So that means that if a model changes, so that the marginal contribution, the feature value increases or stays the same, the Shapley values also increase or stays the same. And from consistency, you can see that the axioms of additivity, dummy, and symmetry follow. So SHAP values have then all the properties of Shapley values, and in addition, we have the missingness. You can also calculate SHAP values for all observations and create a matrix out of that. So this gives then one per row observation and one column per feature. So these are the observation and these are the features, and you just get for each observation and each feature, you get the Shapley value. And by that, we can also interpret the model globally by looking at the values in the matrix. So for example, we can calculate feature importance, but because Shapley values can be, or SHAP values can be negative and positive, we take the absolute values because we don't want to have these effects canceling out. And we sum that over all observations. And here we see that, for example, temperature is an important variable, and also here. So here the interpretation is that the features temperature and year have the highest influence on the model prediction. But compared to Shapley values, we don't see any effect direction. That's because of the absolute value. but a feature ranking similar to permutation feature importance. But compared to permutation feature importance, the Shapley feature importance is based on the model's predictions, and the PFI is based on the model's performance, so on its loss. So that's a little bit different interpretation. We can also create these summary plots. Here we combine the feature importance with the feature effects. So each point in that plot is a Shapley value for a feature and an observation. So we have the features here, and the points are then for the observations. And the color here represents value from low to high. And the overlapping points are usually jittered. So we see in this plot that low temperatures have a negative impact. So here low temperatures are coded in blue, and the Shapley values are negative, meaning they have a negative impact. And high temperatures are red, and they have positive SHAP values, so they have a positive influence. And for year, we just have 2-point clouds, because year only takes the values 2011 and 2012. And the red ones are the one with high values, so here on the right. So that means that in 2012, the SHAP values are positive, meaning that year has a positive influence on those because the number of rented bikes increases over time. And for humidity, for example, it's the other way around, that the positive values of humidity, so for example, when it's raining, then you have a negative impact on the number of rented bicycles. And if you have low values for humidity, then you have a slight positive effect. And you could wonder why these values here, for example, are not always the same. And the reason is that the interactions with other features are split up to the different features. And that's why we don't have the same SHAP value for all the observations of with the year of 2011, for example. We can also plot a dependence plot. So we plot a feature, here it's the temperature here, and the SHAP value on the vertical axis. And this gives us the information that for increasing temperatures, the SHAP values are higher. So more bikes are rented, and the effect on the bike rental is positive. Of the temperature is positive for large values of temperatures, but if it gets too hot, the bike rentals decrease. But we still have a positive effect compared here to the very low temperatures. But it's a little bit smaller than here for the high ones, for the high but not too hot ones. So we can also color this plot by a second feature. So here by the season, and we see that in winter, temperature has not so much of an effect, but in summer, it has a stronger effect on the number of rented bicycles. So SHAP values have all the advantages of Shapley values. And so they also have the nice theoretical foundation, and that they are quite easy to interpret for single observations. And they unify the field of interpretable machine learning, the class of additive feature attribution methods. So we didn't discuss this here, but if you choose the right kernel, then you can show that LIME and SHAP can be equivalent in some cases. So that unifies this additive feature attribution methods with the Shapley values based on game theory. And SHAP has a fast implementation for tree-based methods. That's called TreeSHAP. And we have seen several global interpretation methods. And that's also a nice feature that we have different, quite easy to interpret plots. But also all the disadvantages of Shapley values apply to SHAP. So for example, it is quite slow if we use KernelSHAP. TreeSHAP is quite fast, but it only works for tree-based models. So we won't cover it here because our focus is on model agnostic methods. And KernelSHAP ignores feature dependence. So that's the extrapolation issue as we have seen with most of the methods we covered.